Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this lecture, we are going to discuss some extra implementation details that we are going to need for implementing Deep Q-Learning for Breakout. First, we talked about how the input is a lot bigger than we're used to. Recall that we're stacking 4 frames as the state. The frame is of size 210 by 160 by 3, but we can get rid of the 3 and make the image grayscale. So in total we have 210 by 160 by 4 for the size of each state, which is 134,400 inputs, which is a lot. The nice thing about old Atari games is that their graphics are pretty simple, so you can downsample the image without losing any information at all. In fact, there are even parts of the image that we don't really need for making decisions at all, so we can crop the image too. Let's inspect the frame so you can see what I mean. First, you'll want to import Gym and get the environment, which, if you don't know, is Breakout for this example. And then get the first state by doing env.reset. Remember that env.observationspace.sample will just give you uniformly sampled pixels, so that won't help. Next, you want to import matplotlib so we can plot the image. You'll see the first frame of Breakout. So we can see that the top of the frame and the bottom of the frame underneath the paddle we don't really need. I would recommend trying this and zooming in to see which parts you can crop out. So I chose pixel 31 and pixel 195 along the height dimension, so let's crop that out and see what it looks like. You can see that by doing this, we'd still have all the information we need to play the game. Next, we mentioned downsampling. So let's try that next. Luckily, SciPy has a function specifically for downsampling images called imresize. Notice how 105 by 80 is half the size of the original. This looks kind of blurry, but not for the reason you think. The reason is because image downsampling isn't just subsampling the original, it does some fancy math in between. So we can do better by choosing a different interpolation method, specifically nearest neighbor. So this looks much better. Finally, it's kind of convenient for us to treat images as squares with equal width and height. You might wonder if distorting the image like this might result in us losing information, but this seems to look okay as well. The other image processing steps, which are grayscaling, is just taking the mean along the color axis and scaling the pixel values to between 0 and 1, which are all stuff you've seen before. All these steps help us save space in the experience replay buffer. The next change we are going to talk about is using built-in TensorFlow layers. Recall from convolutional neural networks that in order to connect the convolution layers and the fully connected layers, we need to flatten the final convolution output. But to make the first hidden layer weight the right size, we need to know what size the final convolution output is. This isn't a trivial task in general. In fact, we spent an entire lecture on it. So using built-in layers helps make this less painful. In addition, these are part of the official TensorFlow library, so they are going to go faster than anything we build. Speed really matters here, so it's good to use built-in stuff if possible. TensorFlow has functions for both convolutional and fully connected layers. Next, because we're using built-in TensorFlow layers, that means we'll have less control over what they do. In particular, we were previously using the params instance variable to help us copy the main network over to the target network. But built-in TensorFlow layers don't have a params instance variable. To solve this problem, we need to use what is called a scope. By giving each network its own scope, all the variables we create in the network will have names that are prefixed by the name of the scope. This will help us find the variables for each network when it comes time to copy them. Next is a minor detail, but worth at least mentioning. In the original DeepQ learning paper, they updated epsilon linearly starting from 1 down to 0.1 over some number of steps. After that, they kept epsilon at 0.1. So we'll also take this approach. If you want to know the exact hyperparameters they used, you are encouraged to read the paper. You are of course encouraged to tweak them as well. So keep in mind that what you see in the coding videos today may not be what's officially in the repo in the future. This is why you should always git pull so you have the latest version.